Okay, so welcome everybody to today's TYC tutorial. This is following on from last week. So last week we kind of gave a brief introduction to the many-body problem and went through Hartree-Fock theory and the uniform electron gas. This week we're going to be talking about Thomas Fermi theory, which is a preliminary to understanding density functional theory, which will be the other thing that we're tackling. So as with last week, my plan would be to give a brief overview of what was in the videos and in the lecture notes, just to sort of refresh your memories, and then for you to be able to ask questions or discuss things. But before we start, is there anything that anybody wants to raise at the beginning? Any questions from the videos or the notes that you had already, or anything that you wanted to bring up? Okay, so I've got a quote from Tigran saying, can I go through the derivative? Tigran, can you confirm, is it derivative or derivation you want of equation 58? So derivation. Okay, so how do we get equation 58? So this is looking in the notes that were posted, and this is in the functionals section. So I will start to share my screen in order to go through that derivation. Just before I do, does anybody else have any questions? Because once I share the screen, Zoom disappears and I can't see the chat. So if you're going to have a question after I've gone through this derivation quickly, then please just sort of stick something in the chat right now if you can, or unmute and say something. You're very welcome to do either. Okay, I've got deafening silence, which I'm taking to mean that no one has any other questions. So what I'll do is I'll share my screen and I will go through a brief derivation of equation 58. And then I'll start in on the summary. When I'm going through the summary, please do unmute yourself and stop me if there's something that you don't understand or something that isn't clear or a question you'd like to ask. That's probably easier than me trying to keep an eye out for the chat. Now let me see if I can find it. There we are. Okay, so you should all now be able to see my notes. So we're just going to start with a brief derivation of equation 58. I'm assuming you can all see my screen and you can see what I'm doing, so please let me know if that's a problem. So equation 58, well, let's start earlier with equation 49. Again, this is in the appendix in the notes under functionals. So equation 49, we have a functional e of f of x, which is equal to the integral f of x prime over the magnitude of x minus x prime dx prime. And I hope that you recognize that equation. It's a one-dimensional version of the Hartree energy. So then the next thing that we need is equation 53, which gives us the functional derivative. So equation 53 shows us that delta E is equal to twice. Actually, there should be a double integral sign in that first equation. So equation 49 really should have a double integral because it's got two functions, x and x prime, of f of x prime over x minus x prime delta. Yes, in fact, I need to, sorry, no, that's gone wrong. Sorry, that should be a dx prime. And then I'm going to put a square bracket around this and then put a delta f of x dx. Now notice the reason that this is, we've got a factor of 2 out of the front of this equation is because there are two ways that we can take the derivative. the variables dx and dx prime in the integral in equation 49 are they're oh, I can't remember the word. There are variables which are integrated out, and therefore they're arbitrary, so we can swap them around. So there are two ways that we can make that derivative, delta E, that we're seeing here in equation 53. And then what we need to do is we need to work out the functional derivative, and we've defined in equation 54 that delta E is equal to the integral delta E over delta F of x, delta F of x dx. And therefore, by comparing equation 54, and let me do this in a sort of a greenish color, what we're going to see is that the delta E by delta F of x in equation 54 has to correspond to this square bracket in equation 53. And so what we find just by comparing those two equations is that delta E by delta F of x is equal to, and the two here should also be included in there, is equal to twice the integral f of x prime over x minus x prime dx prime, which is equation 58. Does that make sense? Bear in mind, I can't work out how to make Zoom show me chat at the moment. So if you could maybe unmute and say if that makes sense or not, that'd be really helpful.
Hi, can you hear me?
Yes, I can hear you.
Yes, but I was more referring to how you actually get the derivative. See the double integral there from 49, because it says that the fourth example is not quite straightforward, and you might like to verify that's correct. And,
right. Okay, you were wondering how we go about that.
Yeah. Okay,
so I mean, effectively, what you've got is when you're wanting to take you're looking at a small change in E. So okay, let me maybe work this out. So delta E has to include changes. We have to think about all of the changes you can get in delta E from changes in the function delta F. Okay, that's the starting point. But then notice that what we have, so we have E is equal to a double integral f of x prime over x minus x prime dx prime. So now there are two ways that we can think about how E changes in response to a change in the function. So we can have the first response is that first f of x, and the second response is that second f of x. And because the dx and the dx prime are just variables of integration, so they're arbitrary, we have to consider both of those changes. And so when you rearrange, what you end up with is, so instead of ending up with a f of x, delta f of x prime, and an f of x prime, delta f of x, you can just sort of swap the labels around and end up with the twice that you end in you get in equation 53. Does that make sense?
Yeah, perfect. Thank you.
Okay, all right. Great. So yeah, functional derivatives are not trivial things to understand, and we don't give huge amounts of detail. Okay, so having gone over that, let's now turn to Thomas Fermi theory, just to give you a brief overview of Thomas Fermi. And really the key thing that I wanted to bring out, the key idea that I want you to take away, is this idea that you can get the total kinetic energy for this system that we're considering, which has a non-uniform electron density, by integrating over the entire system. So we're taking this formula alpha h bar m rho to the 5/3 sorry, I want to put a rho of r because that needs to depend on position, to the 5/3 dr. And so what we're using here is that the kinetic energy per unit volume, or let's say the kinetic energy density, that's a much better word for that, is just alpha h bar over m rho of r to the 5/3. And that's the kinetic energy density for a uniform electron gas of density rho. And so the big leap that Thomas Fermi theory makes is to say, well, then let's just integrate over every point in the system and assume that by doing that, we will get the kinetic energy for the whole system. And this is something that we'll see again in the interacting kinetic energy, and it's something that crops up in DFT as well. So that's the key kind of conceptual advance, is to say that by taking the kinetic energy for each point in the system and integrating, we can get the total. And the implication of that is that actually what really matters is the density. And if you go through the derivation, you will get to equation 8, which I'll just repeat for simplicity, which shows us that we've got this condition. We've got 5 alpha h bar squared over m rho of r to the 2/3 plus the potential V of r is equal to mu. Remember, mu is some constant. And so what we're saying here is that the density, we will find the ground state. Tigran, I think you may still have your microphone on. Could you just mute that? So if you go to find the ground state, what we do is we have to arrange rho of r in such a way that this condition is fulfilled throughout the system. And you know, we started the notes and the lecture with a very sort of simple kind of toy model where you just split a box into 2 areas, and we find we get exactly the same solution here. So that's the Thomas Fermi theory idea for a non-interacting electron gas. And we've got the external potential V of r, and that in turn then determines rho of r. But actually what Thomas Fermi theory is doing is it's assuming that you can do it the other way around. In other words, you can determine all of the properties of the system from the density. If everyone's happy with that, then I will move on. If you've got questions, then do unmute and shout at any point, please. Okay, so the next thing is where we then introduce interactions. And again, we extend the idea that we had from before. And so we have the idea that the Hartree energy is given by a half times the double integral of rho of r prime over 4 pi epsilon naught r minus r prime dr prime, and the exchange energy is given by the integral over the exchange energy for the uniform electron gas, which is just minus beta over 4 pi epsilon naught integral rho of r to the 4/3 dr. So that's doing the same thing that we did for the non-interacting gas, where we said that we're going to integrate the kinetic energy over the whole system. Now we're integrating the entire electron-electron interaction. And if we follow this through, then we find that the condition that we need to fulfill to find the ground state, the minimum condition, is simply the following. It is that 5 alpha h bar squared over m rho of r to the 2/3 plus V effective of R is equal to mu, where V effective is given by V of R plus V Hartree of R plus an exchange potential Vxc of R. And that's a really important equation. It's something that we need to take on board, because if we compare that equation with the equation up here, so in fact let's give these two numbers. So that's equation 8, and this new one is equation 16 in the notes. We see that they're effectively the same. It's the same mathematical problem that we're trying to solve. It's just that V of R for the non-interacting gas has been replaced by V effective of R for the interacting gas. And this goes to the heart of what makes density functional theory so simple to implement, which is that we can solve an interacting problem by thinking about a non-interacting system with a different potential. And so all of the interesting physics is now bound up in these two terms here, this V Hartree and this V exchange of R. There's one more thing that we need to mention here, which we also touched on briefly when we were looking at Hartree-Fock theory, which is the idea of self-consistency. Once we introduce interactions between the electrons, we note that V Hartree and Vxc depend on rho. And we would only find rho of R by using those two potentials. So there's going to be some kind of looping backwards and forwards. So you have to have some kind of input guess for the charge density. You then create the potentials. From the potentials, you solve for the charge density, and then you have to continue around until the charge density and the potential are consistent with each other. And I will say again that this is a non-linear process, and if you have any experience of trying to do DFT, particularly on metallic systems or systems which are have got very different dimensions, so something which has got a very long dimension in one direction and a very small dimension in another direction, these can actually cause serious problems in terms of convergence, and this nonlinear process can become quite difficult to manage. There's been a huge amount of research on it, as you might imagine, and most of the time it works just fine, but it's not trivial and it's not always certain. That's really all I want to say on Thomas Fermi theory. It's not of huge practical importance. It has been used recently in an approach called orbital-free DFT, which I can talk about towards the end of the tutorial if you're interested in. But really, it's included in these lectures simply because it gives you a nice insight into how we go about doing DFT. So does anybody have any questions at this point about what we've done so far?
Can I just mention, I think there's meant to be 1/3 at the start of equation 16 and equation 8. You've got 5, I think it's 5/3, isn't it?
Oh, it is, yes, thank you very much. Spot on, well done. Yeah, it is 5/3, there we go. Gone back and fixed. Yeah, excellent. Not sure where I lost that. So apart from my stupidity, is there anything that needs fixing? Anything needs exploring further or explaining?
I have a question. I don't know if
Yeah,
it's a bit of a silly question because I don't really have much background, but we're calculating the ground state energy.
Yeah.
When we're using it in practical systems, is the ground state energy what we care about?
Okay, absolutely. That's a really good question. So in general, yes, the ground state energy tends to be what we care about, because that then enables us to do other things. So for instance, once we've got a ground state energy on a trivial kind of level, it means that we can compare the energy of different structures. So if you were interested in different sort of surface reconstructions or different defect structures, then you could work out which one had a lower energy. But more interestingly, once you've got the total energy, you can generally write down analytically the forces on the atoms. And if you're dealing with a solid state system, you can also calculate the stress on the cell, the unit cell, the simulation cell in which you're doing calculations. And that then means that you can move atoms and move the unit cell. And so that opens up the possibility of doing a structural relaxation. So you can find the lowest energy structure. It opens up the possibility of molecular dynamics, which gives us insight into free energies and viscosities and all sorts of properties.
And when the system is not at 0 Kelvin, you could still be at the ground state, or you're necessarily going to be at an excited state if you have. Okay,
yeah. So again, important and interesting question. So typically what we assume is that the electrons are in the ground state. You can introduce electronic temperature. So typically what we'll do, and we'll talk about this in a minute, is that, for instance, the charge density rho of R is generally given by a sum over some kind of eigenstates of psi I of R squared. And if you're worried about partial occupancy, which you might well be if you have a metallic system, then you can add into there an occupation number, Fi. And so at 0 Kelvin, Fi is equal to 0 or 1. And at T greater than 0, Fi is just the Fermi function of epsilon I, comma, kT. So in terms of the electronic structure, yes, absolutely, you can include the effective temperature. It really depends on the system that you're dealing with. And if we're interested in the sort of the free energy of the system of atoms, then that's the kind of thing that you deal with by doing molecular dynamics.
Okay, thank you.
Okay, and the whole question of density functional theory and excited states is a different one. DFT formally is only a ground state theory. People frequently use DFT excited states and unoccupied states in order to deal with the systems, even though formally it's not necessarily guaranteed to be correct. There are also there's time-dependent density functional theory, which gives you excitation. People use DFT as the input to more accurate approaches, such as GW or BSE, the beta-Salpeter equation. So it kind of opens up into the whole zoo of problems, which certainly I don't have time to talk about today, I'm afraid.
Okay, thank you.
You're welcome. Okay, so let me go on to DFT. DFT, or density functional theory. So the first thing that we did was we did some formal maths. So you've got the Homocone theorems. The first of those, which effectively what it allows us to do is it allows us to map from rho of R, the charge density, to V of R, the external potential, which then gives us the ground state total energy wave function and the ground state wave function and the total energy. And this idea of mapping from rho to V is at the heart of DFT. It's fairly clear from all of the stuff we've done before that an external potential will determine the charge density. It was that leap to be able to reverse that mapping, which allowed DFT to do everything, because now we can say that the fundamental variable is rho. The formal statement here is simply to say that if you've got two external potentials which differ by more than a constant, in other words, we have done more than just shifted the zero, then they will give rise to different densities. And the proof of that is in the notes. So the second Homocone theorem simply put onto a formal footing the idea that if we define the ground state energy to be the integral of rho of R, V of R, so that's the interaction between the electrons in the external potential, plus this F of R, this functional, which encapsulates all of the electron-electron terms, and we minimize it with respect to WRT rho of R, that will give us the ground state. And that, again, that's just essentially putting onto a formal footing the whole idea that we're doing here, which is we write everything in terms of the charge density, we then minimize the energy with respect to the charge density, and that allows us to find what we're looking for. So that's the Homocone theorems. They're not often used. It's good to know that they're there and to understand how they work, but I don't think they're used very often. And then from there we have the fact that the ground state energy, the ground state, is the integral between rho of R and V of R, plus then three other terms, the kinetic energy term, the Hartree energy, and what we call the exchange correlation energy. The Hartree energy we know how to do. That's classical. So let's tick things off that we know how to do. The interaction between the electrons and the external potential, again, we know how to do. That's again a classical electrostatic interaction. it's important to note that the kinetic energy, we're going to end up writing this in terms of the kinetic energy of non-interacting electrons. And notice again that we're using this idea of mapping a system of interacting electrons onto a system of non-interacting electrons. So having done that little map and defined that that's what our KE is, we can now find the total kinetic energy. And that leaves us with this term at the end, the exchange correlation energy. Formally, this transformation from a many-body system to this density functional theory system is exact. We've made no approximations in doing this. The problem is that this functional is unknown. And so we have to approximate. And this functional will contain 3 different contributions. The first contribution is the difference between the kinetic energy of an interacting electron gas and a non-interacting electron gas. They are different kinetic energies. The second contribution will be the exchange. We saw the exchange written formally for Hartree-Fock. And the third contribution will be the correlation. Correlation, as we talked about last week, is a slightly slippery idea, but basically it's just all of the other many-body effects that aren't captured by Hartree-Fock. And so those are the 3 things that go into that EXC, and we have to make an approximation. Having defined that total energy, we can then do the usual process of optimizing and minimizing to try to find the ground state, and from that we can derive the Cohn-Sham equations, which are what are actually solved when you do a DFT calculation. And here we have that minus h bar squared over 2m del squared, that's the kinetic energy, plus the effective potential, the F of R acting on psi I of R is equal to epsilon I psi I of R. And just to be complete, the effective of R is equal to V of R, the external potential due to the nuclei, plus the Hartree potential, plus the exchange correlation potential. And when we've done that, and when we've solved for those equations, we can then write rho of R is twice the sum over the occupied states of the square modulus psi I of R. And as before, as I've mentioned, we have to do this in a self-consistent manner. So we have to guess an initial charge density. And that gives us a potential which allows us to solve the Cohn-Sham equations for the initial wave functions, which then allows us to generate a new charge density, and we can then go round in a loop. And as a sort of just a very, very brief touching on the idea, because I think that Tom is going to talk about this later, just to say the local density approximation, the LDA to the exchange correlation energy, is following very much in the footsteps of Thomas Fermi theory. We write it like this, so it's a functional of the charge density, and it's given by the integral dr of rho of r epsilon x c0 of rho of r. And epsilon xc, this is the exchange correlation energy for a homogeneous electron gas. That can be calculated extremely accurately using approaches such as quantum Monte Carlo. And the most famous example of this is called the Sepeli-Alder parameterization. So Bernie Alder actually died in the last month or so. He was a huge figure within computational and atomistic modeling. And David Sepeli is a very big name in the quantum Monte Carlo field. And they did a series of calculations for the exchange correlation energy for a homogeneous electron gas at different densities. And you can then derive a fitting, which allows you to calculate EXC for any charge density that you want to use in a DFT calculation. So that's a bit of a whistle-stop tour of what was in the lectures and what's in the notes. Hopefully that's given you a bit of a refresher. Are there any questions, things you wanted to bring up from either the notes or from what you've heard just now?
Hi, yeah, I have a question. I was just wondering, what is the external potential in terms of like a physical meaning, and why do you
Okay.
refer to it as external?
Okay, absolutely. So let me actually write a little bit here, because that's a very good point. So we write V of R, we call the external potential. We say external because it's external to the nuclei. Sorry, it's external to the electrons. So it's a potential from the outside, which has nothing to do with the electrons. So typically it will be the nuclear electrostatics term. So for instance, if we had a set of ions, we would write something like V of R is equal to a sum over capital I, and I is going to index the ions, and we'd have something like Zi over R minus Ri. And okay, let's just be careful here, because we want to have an E over 4 pi epsilon naught. And we would have to be a little bit careful about signs. We'd have to work out whether which sign we're letting the ions be. But that's the simplest statement of what V of R is. Does that make sense?
Yeah, thank you.
Yeah. Okay. Something that you'll discover if you do if you take the physics approach, let's say, to DFT, is that quite often we don't deal with all of the electrons, and we also don't deal with this nuclear potential, because the nuclear potential is quite nasty. You can see that if R is equal to capital Ri, then that goes to infinity, or rather, it should be minus infinity. So actually, we do need a minus sign at the front there. And so there's an issue there, which is dealt with in various different ways. What a lot of physics-based codes, solid-state codes, do is they take the hard nuclear potential, so this 1 over R term, and they take the core electrons, and they combine them into a single softer potential, which is called a pseudopotential. And that replaces this 1 over R term. But again, it's the same thing. Each ion has an associated potential, and we just map that into space. Okay, anybody else got questions?
Hi, David. I had a question.
Yeah, go for it.
So at the end of the section on Thomas Fermi theory, you say that the non-interacting ground state under the effective potential is exactly the same as the interacting ground state under the actual potential V.
Yes.
Yeah. So I was wondering, is that still the case in when we go on to density functional theory, in that there is an exact mapping from the non-interacting ground state to the interacting ground state, or is that only because of the assumptions built into Thomas Fermi theory?
Yeah, no. So formally, that mapping is still there. Mm-hmm. Before we try and think about what EXC might be, that mapping is still formally exact. What we've done is we've put all of the interacting terms into EXC. But yeah, it's an exact mapping, and there's no approximation there. It should give you the same answer if you knew the form of the exchange correlation functional. And the problem is that we don't know what that is.
And is that part of that's not part of one of the Hohenberg-Kohn theorems, is it, or is it Kohn-Sham formalism?
It's so it's really I think probably I would say it's the Kohn-Sham, because Kohn-Sham is where we bring. I would have to check the papers to be completely sure, but I think it comes from Kohn-Sham, because that's where we're bringing in the idea that the kinetic energy is the kinetic energy of the non-interacting electrons. That's the kind of the key point with that mapping, and I suspect that's in the Kohn-Sham equations.
Great, thanks.
Okay. Yeah.
And one other follow-up
yeah.
was so I just wanted to make sure that I have the right approximations in my head for Thomas Fermi theory. So for that theory, the two main approximations are that the of course the kinetic energy is the same as that for the non-interacting uniform electron gas using the same kinetic energy density, and it's the other one is that it's the exchange energy is the same as the integral of the exchange energy density for the uniform electron gas as well. Are they the two main?
Yeah, that's the key point of Thomas Fermi theory. Is this idea that you can take an integral over the charge density over the whole system, and at each point in the system, the only thing that determines the kinetic energy or the exchange energy is the charge density at that point.
Mm-hmm.
So, and the same is true in the LDA. So the way that the LDA works, which is down here, again, you can see that we've just got this exchange correlation energy, this term here, that only depends on the charge density. Now, people discovered fairly quickly that the LDA is not a particularly good approximation. It's remarkably effective for how simple it is, but it isn't particularly accurate. And so people started to ask questions like, what happens if we think about the local gradient in the density? And so that gave rise to what are called generalized gradient approximations, where you take into account both the value of the density and the value of its gradient. So things like PBE and BLIP are famous examples of that. In the last 10 or 15 years, people have kind of thought, hey, let's go to higher derivatives. And so there's a thing called the kinetic energy density of the electron gas, which involves obviously a second derivative. And so that when that's included, people are talking about what's called a meta GGA. So it's kind of going beyond GGA and bringing in the second derivative of the local density. There's a particular meta GGA which seems to be very effective called SCAN. And then there are other things that people have done. So for instance, they've noted that, and this is something I meant to mention actually, when we talked about Hartree-Fock, I pointed out that there was an exact cancellation between the Hartree energy and the exchange energy when the two contributions to the density are the same. You remember there was that point where you've got an R, you started with both sums being I not equal to J, and then we said actually because they're exactly the same we can cancel them out. That exact cancellation doesn't exist in DFT. So in DFT, let me in fact just write this, the Hartree energy contains an interaction between an electron and itself. And that's not good. It's called the self-interaction error. And it's cancelled in Hartree-Fock theory because of the exchange, but it's not cancelled in DFT because the exchange in DFT is written in terms of charge density, just as it is in Thomas Fermi theory. And that's actually known as being one of the biggest errors in DFT. And so there are people who've tried to fix that. One of the ways they fixed it is by saying, actually, let's not do a Thomas Fermi-like charge density integral for the exchange energy. Let's actually do a Hartree-Fock-like exchange energy calculation using the Cohen-Sham orbitals. And that brings in what people call hybrid functionals, because you're bringing in sort of Hartree-Fock and DFT, and so you're mixing between the theories. And you can carry on adding more and more kind of complexity and intensity to your approximations. And there are thousands upon thousands of functionals out there nowadays. Sorry, that was quite a long and digressive answer to your question, Sean.
No, it's great. It's a nice overview of the different functionals out there. Thanks.
No problem. So anybody else, any other sort of questions or even comments or thoughts?
Hello, can you hear me?
Yeah, I can hear you.
Yeah, sorry, I have a question that I think might sound stupid, but going off of the question regarding external fields and the meaning of so just to clarify, does external field mean, or external potential, does it mean any interaction that is non-electron-electron?
Yeah. Okay. Sorry. So your microphone is cracking up a bit. Basically, I think you're saying, could the external potential be anything that's not to do with the electrons? Is that right?
Yeah.
Yeah. Yes, it can. So, for instance, one of the things that you can do is, if you're interested in, let's say, the effect of an electric field on a molecule, then you can have an external field. Obviously, that introduces all sorts of interesting questions. So you've got the effect of the external field on the electrons themselves, and so that would have to be added into that potential. You then also have the fields acting on the ions, the ionic cores, so you'd have to consider those. And if you're using a solid state DFT code, then the idea of an external potential brings in all sorts of problems, because solid state codes almost universally use periodic boundary conditions. And so you can't apply a single ramping potential. You can't apply a potential difference across a periodic cell without having a drop of somewhere. So that can cause other issues. But you're absolutely right. Sorry, the simple answer to your question is yes. The external potential includes anything that isn't the electron-electron interactions. So electron nuclei, external field of some kind, anything else like that.
All right, perfect. Thank you very much.
Okay, no problem.
For that equation where you say that we're making no approximations, that it's exact, I think at the end of the Thomas Fermi theory. Are we not? That one. Are we not assuming that the nuclei are fixed?
Okay. Yes. Absolutely. Yeah. No, you're quite right. So, in most approaches to electronic structure, so Hartree-Fock or DFT, we start with the Born-Oppenheimer approximation. In other words, we decide that we're going to separate the electronic and the nuclear degrees of freedom.
Is it ever not reasonable to approximate that?
Yes, there are some very important cases where you have to allow electronic nuclear interaction. So anytime when, so particularly with hydrogen, you can have some very interesting effects, and particularly where you've got some very strong excitations, you can have all sorts of things. And in fact, anytime when you've got current flowing in a smaller number of atoms, you can again have a very strong interaction between the electrons and the ions. So in all of those cases, you sometimes have to consider very carefully what's going on there. Excited states as well, electronic excitations can have some significant effects. So if you imagine hitting a molecule with a laser beam, exciting an electron, that electron then has energy. The two ways that it can lose that energy, one is radiative, and so that just emits a photon. The other one is non-radiative, where it couples into the vibrations of the molecule. And there you've got a very strong interaction between the electrons and the ions. Solving those kinds of problems is much, much more complicated. And you have to sort of think about it in a number of different ways. So the first question you have to ask yourself is, are my nuclei behaving as classical particles or quantum particles? Provided they're not hydrogen, generally thinking of the classical is a fairly good idea, and that's known as the Ehrenfest approximation or the Ehrenfest approach. And then there's the whole question of, can I separate the electronic degrees of freedom from the nuclear degrees of freedom, which is the Born-Oppenheimer approximation. And they're two very different things. So you can have quantum nuclei, which are sufficiently slow moving or sufficiently localized that the electrons can still be considered in the ground state. And you can also have, though it's a bit of a mess in terms of formal quantum mechanics, you can have classical nuclei which are affected by the electrons and which affect the electrons themselves, so that the electrons are no longer in the ground state.
Okay.
Okay, sorry, that's again quite a long.
No, it sounds complicated, but
so yeah, you're absolutely right. so long we have assumed the Born-Oppenheimer approximation in that equation,
Yeah.
and generally that's a good approximation to make.
Mm-hmm.
There are some important situations where it's not a good approximation. That I was talking about that because I think it's important that you're at least aware of that.
Yeah.
But most of the time, it's fine.
Okay. Thank you.
Okay. Anyone else? Okay, at least for the moment, I'm going to stop sharing my screen so I can just quickly check the chat box. Okay, so everybody can message. So unless anyone has any questions, then we're coming up to 10 to 2. So if you have questions, please do ask. I'm very happy to answer any more, but otherwise, if I don't hear anything in the next couple of minutes, we'll kind of call an end. And that's the end of my part of this lecture course. You'll be getting someone different next week. No more questions? Okay, fantastic. Well, I think that's probably a good point to stop. If you do have other questions, please feel free to email me, david.bowler@ucl.ac.uk, or ask Karen if you can't remember. And I hope that you have a good week and enjoy next week's lecture.